In previous videos, we looked at two types of errors in statistical hypothesis testing. In this video, we'll look at the related concept of statistical power. Let's start by looking at a scenario. The 2018 race for New York State's 22nd congressional district was extremely close. Anthony Brindisi, a Democrat, received 127,715 votes, and Claudia Tenney, a Republican, received 123,242 votes. So Brindisi received 50.89% of the vote to Tenney's 49.11%. That's a difference of just 1.78 percentage points. The two candidates will be competing again. Suppose you want to conduct a poll to try to predict who will win the race. How many people do you need to survey to detect a difference of 1.78 percentage points? Answering this question requires thinking about something called statistical power. Statistical power is the probability that a hypothesis test rejects a false null hypothesis. It's also equal to 1 minus beta, where beta is the probability of making a type 2 error. For example, let's say you want to predict the results of the next election between Brindisi and Tenney. So the parameter would be the percent of voters who vote for Brindisi. And we'll call this parameter pi. So the null hypothesis is that Brindisi won't have an advantage, or that pi is equal to 50%. Now, let's suppose that the percent of people who would vote for Brindisi would be the same as in the last election. So the null hypothesis is false. What is the probability that your 500-person sample would lead you to reject the null hypothesis? Let's build a model to investigate this. First, we'll build a sampling distribution based on the null hypothesis. So we'll set up a model where 50% of the votes go to Brindisi and sample 500 voters at a time. Then we'll repeat this many times. Here we'll do 1,000 repetitions. Then we'll build a sampling distribution based on the actual value of the parameter. So we'll set up a model where 50.89% of the votes go to Brindisi and sample 500 voters at a time. Then we'll repeat this many times. Here we'll do 1,000 repetitions. Next, let's look at the sampling distributions generated by each of these models. Here's the sampling distribution based on the null hypothesis that 50% of the voters would vote for Brindisi. And each dot represents one simulated sample of 500 voters, assuming 50% of all voters would vote for Brindisi. So what we want to figure out is which statistics would lead us to reject our null hypothesis. So in this sampling distribution, we would identify the 5% of statistics that are furthest from the hypothesized value. So statistics that are less than 45.8% and greater than 54.2% would lead us to reject the null hypothesis. So now we know which statistics would lead us to reject our null hypothesis. Let's take a look at the sampling distribution based on the actual value of the parameter. Here's the sampling distribution based on the actual value of the parameter, which is 50.89%. So each dot represents one simulated sample of 500 voters, knowing that 50.89% of all voters would vote for Brindisi. And what we just figured out is that statistics that are less than 45.8% or greater than 54.2% would lead us to reject our null hypothesis. So any statistics in this gray area would lead us to fail to reject the null hypothesis. And statistics in this green area would lead us to reject the null hypothesis. And we can compute these probabilities. So if we combine these probabilities, there is a 7% probability of rejecting the null hypothesis. In other words, there is a statistical power of 7%. So this is what statistical power is, and there are several ways we typically use this concept. Like type 2 error, statistical power is affected by the value of the parameter, the sample size, and the value of alpha, the probability of making a type 1 error. So the questions we asked are based on imagining that 3 of these values are constant. For example, in the case of the election, we might say if the parameter is 50.89% and we sample 500 people and use an alpha of 5%, how much power will our survey have? Or, if we want 80% power and a sample size of 500 and an alpha of 5%, then we can ask, what is our margin of error? What is the smallest amount of variation we can detect? Or, if we want 80% power and the parameter is 50.89% and alpha is 5%, then we can ask, how large of a sample do we need to detect the false null hypothesis? Or, if we want 80% power with a 50.89% parameter and a sample size of 500, then we can ask, how much error would we need to allow? And we can answer each of these questions by adjusting the simulation and, if needed, trying out several values to estimate the margin of error, sample size, or amount of error.